Alright, welcome to the tutorial, guys. Today we are looking at AS1170.2, which is wind actions. This is part of the 1170 series of standards, which is all about loading on structures. So point 0 is the general, point 1 is your live loads and service loads, 2 is wind, I think 3 is earthquake, 4 is snow, and so on. This one is, if you become a structural engineer, you will get intimate with this code. It's difficult to work with, and it's complicated, but you can do it. So today we're going to sort of go through it initially. I'm going to skate over lots of the complexities, so this is like a rough introduction. There's a lot more that goes into it. So first I'll talk about the scope, which is basically what does this cover, and what are you allowed to do with it. So the scope says you're allowed to use this for buildings which are less than or equal to 200 meters high. Alright, so it covers everything from small to very tall buildings. Structures with a maximum unsupported roof spans of less than 100 meters. So that covers most of your major sheds. If you're doing stadiums, you might be in a different league. Structures other than offshore structures, bridges, and transmission towers. So pretty much everything I've ever designed that's exposed to wind will be covered by this code. Alright. There is another version called AS1170.2 which is wind loads on domestic structures, which is designed for houses. So it's a cut down, it's a more simplified version of this. But this is what you'll need to get familiar with for your engineering. Okay? So to get, basically what we're going to do is we're going to work through this code. It comes in two parts. The first part is working out what the wind speed is. And the second part is working out what does the wind do to the structure that you have. Okay? So in order to get the wind speed, there's been a lot of data collection over decades by Bureau of Meteorology, and they've collected wind speeds all over the country in all sorts of different circumstances and done statistical analysis on them all. So we can look up and say, if you're in a certain location, what's the wind speed you want. All right. So the first part is then to go to the calculations of the wind speed actions. And what we do is we talk about the site that we have and the wind speed. Now, when we get to that, this is the key equation then which joins the two parts together. That's the pressure, that's the density of air, that's our wind speed squared, don't forget that. That's our C fig, which is all about the shape of the building or structure we're doing. And C dynamic, which is about how the thing interacts and moves with it. Alright, so let's get started, and we're going to look at an example of a certain structure in parks, which is going to be a noise wall, which happens to be the thing under you guys are considering, but we'll also touch on structures and other things. So the first thing we need to do is work out the return period of the wind speed we need. If you go to table or chapter 3 in the code, and table 3.1 has regional wind speed, V1 to V10,000, or is that, yeah, 10,000, and your region, and gives you a number there. And what this is saying is this is the basic wind speed and return period for where you are. So you need to know your site. So there's a map of Australia, and Parks is right about there, which puts us in region A1. Okay? So yeah, write that down, region A1. Okay, get that from map. And region A1, now we need to know the return period of the wind. The return period is, or the annual exceedance probability, is looking at how often does this wind speed come along. And we want our noise wall to stay up in a storm. Well, if we said a year that's an annual exceedance probability, it's going to come along roughly every year, that means every year is a wind going to come along which is strong enough to knock your wall over, right? So that's bad. So we want a higher return period than our design life. So we call the annual exceedance probability, which is the AEP, and that applies to wind, it applies to floods, rain, all that stuff. Annual exceedance probability is a probability that the event we're talking about is going to happen in any one particular year. So if our annual exceedance probability is 1%, that means that this year there is a 1% chance of this storm occurring. Okay? There's a trade-off, obviously, between efficiency of design and how strong we're going to do it, how strong we're going to make this structure. So one of the things you need to do is consider what sort of structure is it. There's 4 categories. There's basically things which fall over and don't harm anybody, which is categorized as farm sheds. I would say a noise wall is one of those. Category 2 is most normal buildings. Category 3 is buildings which can house large numbers of people. And category 4 are things they're called post-disaster recovery buildings. So your hospitals, your nuclear power stations, your emergency services need to be category 4. And if you look up AS1170.2, I think, you will see the classifications of those buildings, and you'll be able to classify what your wall should be, and based on its design life, what return period the wind should be. All right? We're going to go for a 500-year return period, or an annual exceedance probability of 0. What's the inverse of 500? 0.2. Yeah. Okay? 0.2% chance of occurring this year. All right? Now, some on the video, or you guys might already be quibbling with me that that's the wrong one, but we'll take that for this, okay? All right, so we're going for a V500. Out of this table is, if I go down there, regions 1 to 7A, V500 is 45 meters per second. All right. So V500 is 45 meters per second. All right. Now, our wind speed there's an equation here, which is wind speed is, here we go. The wind speed, our design wind speed, is, for our site, is going to equal VR times MD times MZ cat times MS times MT. All right? That's that. We've done that one already. And these ones are just modification factors. All right, and we'll work through what each of those are. We multiply them out, and we're going to get our V, which is our wind speed for the site, for the direction. So the first one is the direction multiplier. MD is a direction multiplier. We turn to a table here in table 3.2. Has a direction multiplier for each region. Region 1A, 1B, sorry, A1, A2, A3, up to A7, and then W. Now, basically what the meteorology department has found is that the wind doesn't blow equally hard from every direction. Okay? So in region A1, those factors go from 0.8 to 1.0. And in the westerly direction, it's 1.0. So that's saying in region A1, which is all that region there in Australia, the wind blows hardest from the west. And from other directions, from the north, for example, it's only 80% as fast as from the west. So if you are designing a building, and you know, if we're doing plan here, and you've got this enormous building like this, that's north, that's south, that's east, that's west, okay? The wind is going to go blow hardest from the west. Okay, this gets me out every time. The wind blows from a direction, it doesn't blow to that direction. Okay? A westerly wind blows from the west, it doesn't actually blow west. Westerly wind blows east. Okay? I'm sorry, that was a convention, it wasn't me. So the wind is going to blow harder from that direction than it is from that way. So if you've got a big structure here, you have to make sure that you've got extra resistance from the western side rather than the other sides, okay? If you're designing a building and you don't know which way around that's going to be oriented, and someone comes along and turns the building 90 degrees, then that messes up all your calculations, okay? So normally, unless it's a big building where it's going to make a difference, and I'm absolutely sure which way it's going to be oriented, I say, someone might spin it, and we take MD as 1.0 all the time. Okay? There you go. That's MD out of the way. Next one is MZ This is called the terrain or height multiplier. And what this means basically is that what does the ground around the region look like? And we've got categories that goes from 1 all the way up to 4. So 1 is an airfield where you've got completely flat area and there's absolutely no resistance to the wind blowing. 4 is in a city, large buildings all around the place, or in a forest, basically lots of resistance to the wind. Okay, and that slows the wind down. If you've got open water, when the wind blows, there's enough waves that actually causes resistance to the wind, so that's category 1.5. And in section 4.2, there's an explanation of what all those categories are. So common 1 is category 2, open terrain including grassland, with well-scattered obstructions having heights generally 1.5 to 5 meters, no more than 2 obstructions per hectare. For example, farmland, cleared subdivisions, isolated trees, uncut grass. Category 2.5, terrain with a few trees and isolated obstructions. It's intermediate between T2, T3, represents terrain in the outer urban areas, that kind of thing. By the time you get up to T4, TC4, terrain with numerous high buildings, closely spaced obstructions. Okay? So you've got to pick what your terrain is. Now, to make it more complicated, back in this building over here, if it was all clear out this way and all obstruction out this way, then the southerly wind would have a different terrain category than northerly wind. All right? So we're already adding complexities to it. Now, in parks where your wall is located, I had a look on Google Earth, and it looks like a fair bit of plain country out there, especially out to the west. So we're going to take a terrain category of 2. Okay? So terrain category 2. Now what you do with that then is turn the page. And then we have to know the height of the structure that we're building. Okay? So if you have a house, there's a house. The height of that structure, how tall is that structure? It depends. Basically, I'd be comfortable saying that is the height of the structure. Okay? You're basically getting a characteristic height. If the whole thing is mostly, the ridge presents a full face to the wind, then in that direction it's going to be the full height. In the other direction, it's down there. So, pick a height. That's about it. All right, we'll take that height. How tall is your wall?
3 meters.
3 meters. All right. So we've got ground, there's your wall, it's 3 meters tall. Okay. And what terrain category did you say? 2. Alright, so then you go to this table, which is table 4.1. And you pick your terrain category, and you pick the height of the structure. And you read off the table, 3 meters or less, terrain category 2, our MZ cat is 0.91. Alright. 0.91. Okay. So we've got 2 of those 4 now. Let's move on to MS. MS is a shielding multiplier. Basically, if you have a building, let's say building, and you put it in the middle of other buildings, they provide some shielding for it. You are not allowed to use trees as shielding because people come with chainsaws and they chop them down or the trees die. A shielding has to be a permanent structure that you're confident enough is going to be there for the life of your structure. And so you can look at the height of the shielding. So if you've got a noise wall and you've got this enormous building like that, there's the wind from that way, that provides quite a lot of shielding. Okay? I suggest to you that you guys probably don't have any shielding. So MS is 1. Okay? There's a table about shielding there. It's table 4.3. Again, you can shield from one direction and not from the other. So your wind speed. You know, you're talking about wind speed. We're working out one wind speed today. You can work out 8 different wind speeds for the 8 cardinal directions for your structure. All right. That's the shielding. There's a little formula there about how big that building is in relation to what you're shielding, that kind of thing. Okay, the next one is the MT, which is the topographic multiplier. This is probably the hardest one to work out. When you have wind blowing over a hill, okay, the wind is blowing all this way. There's the ground, and you have this hill like this. As the wind blows along here, it compresses here, which increases the effective pressure, increases the speed of the wind over the hill. In a steeper hill, you also get a separation area here, where you get some sort of turbulence. Okay? And finally, if you're down here, you've actually got shielding for that hill. And so the topographic multiplier says, what is the height of that hill? What is the length to the height there? Where is your structure? Is it down here? Is it here? Is it right on top? Is it back here? Is it back here? And gives you a factor for that. Now, that factor can be more than 1. Okay, so it can make your wind speed worse. It can be less than 1, which is about shielding behind a hill. Okay, so you notice these ones max out at 1.0. So the conservative option is to take 1.0 for all those. Sorry, MZ-cat can be higher than 1 if you've got a tall structure. But shielding and direction max out at 1.0. So that's the conservative options for those. If we go back to that other table for a second, where we had the heights of the structures, you'll see that the wind speed is higher the taller your building is. So going back to that table there, if your structure is only 3 meters tall, start with the terrain category 0.91. By the time you get to something that's 200 meters tall, you've got 1.29. So you've got a 30% increase in wind speed by going higher. All right. Tall things get blown more. All right, so we have now our wind speed and our 4 categories. Sorry, 1.0, if it's flat ground, less than slope of about 1 in 20, 1.0. I asked Shara, you guys are pretty flat out there. If you built your noise wall on top of a mound of earth, that would increase the wind speed, so you'd have to put something different. If your noise wall is on the ground, which yours is, you can use 1.0. Okay? Therefore, your V, which is your speed, is 45 times 0.91. Can someone put that in their calculator? All right, I will. .91 is 40.95 meters per second. Okay? That's the design wind speed for your wall. All right? Now again, if you have a building and you know the direction, you can have a whole series of different wind speeds for the different directions. Okay, we're considering the wind could blow from any direction, and we're taking the worst case. 40.95 meters per second. All right, so we're going to this equation up here. Our pressure is going to equal 0.5 times the density of air, which is about 1.2, what are the units? Good question. 1.2 kilograms per cubic meter. If you take a cubic meter of air at sea level, you've got about 1.2 kilos of air. All right. So 0.5 times 1.2, which comes out at 0.6 times 40.95 squared C fig C dynamic, and that equals 40.95 squared 0.6. That equals 1006 pascals. Okay. That's the basic wind pressure on the structure. And I say basic because we're about to modify that 1,000 times in this CFIG thing. But that's a number that's going to go into a whole lot of calculations. All right. When you do these wind speed calculations, you should be getting a number in the ballpark of 1,000. If you get 500, that would be very slow wind speed. If you get 1,500, that's something the wind's blowing pretty fast. If you got 50,000, you've made a mistake. If you get 50, you've made a mistake. Okay? All right. That is the first half of the wind speed. Okay, so we found the wind speed. That's the first half of the job done. All right. Now we go to the second half, which is where it starts getting fun. Okay? First, I'll get rid of seat dynamic. If your structure has a natural frequency of less than 1.2 hertz, I think it's 1.2, maybe it's 1 hertz. If it's a flexible structure that moves slowly back and forth, then it actually interacts with the wind, and your life gets more complicated. And by saying more complicated, I mean that there are specialist firms whose sole job it is to work out the dynamic factors on wind structures. It's a very specialist field, and I went to a day-long seminar on this, and I got to the end of it, and I thought, this is for specialists. Okay? It's for people who have access to wind tunnels to back up their stuff. It's because you're talking about the structural rigidity and flexibility of buildings and how they sway back and forth and how the eddies go around that. So, for the vast majority of your life, that equals 1.0. Okay? Unless your structure is big and flexible, you don't need to worry about that. Happy days. All right. CFIG is what we're going to talk about. So I'm going to rub this off. And CFIG is the aerodynamic shape factor for structures and parts of structures. And that's all about section 5 and quite a few of the appendices. And what you do in chapter 5 then is you go through and say, what sort of building have you got? And let's assume that we have a building which in plan looks like that. In elevation, no, let's give it a sloping roof, why not? Okay. In elevation, looks like that. Okay. You work through chapter 5, and you'll see that there is an internal pressure. Let's say the wind's blowing this way. Okay. There will be an internal pressure, pulling inwards or pushing outwards, inflating or deflating that whole building. It's also going to push upwards or pull downwards on that roof. As well as the internal pressure, there's going to be a pressure pushing the wall this way. That's pretty obvious, right? The wind's blowing, the wall's pushing that way. As well as that one, there's going to be a suction pressure pulling the wall off that way. And there's also going to be a little pressure pulling the wall off this way, off the sides as well. And that's higher there and it diminishes as you go along here. As well as that, there's going to be uplift on this roof here. There's going to be uplift or maybe downforce on that roof there. And so you start adding up all these forces in all these different combinations, and that's how you get the wind loads on your structure. And so, for example, table 5.1a is about the internal pressure, and it makes a difference if you have a big garage door there, okay, and that's all sealed up. You get a positive internal pressure where your building basically inflates. And you've got to combine that with the uplift of the wind going over the roof. If you've got the door on the downwind side here, then your building deflates. Okay? When the wind blows this way and blows up over the roof like that, you definitely get a suction there, and you get a suction there. If your roof is quite steep, you'll get a downforce on the roof there and an uplift on that way. If your roof is transition, you can actually get flutter where you have two forces, one up or one down. So you start getting heaps and heaps of numbers start coming out, which is why you guys should get familiar with spreadsheets. Okay? People have written quite sophisticated spreadsheets to track all this stuff. I've got a spreadsheet which I wrote which helps, but it's hard to get a sort of standard spreadsheet because everything's different. Every time you build a structure, it's like, oh, it's got you know, a wall hanging out here, and it's got a bit of carport roof here, which you have to take account for, and that kind of thing. So it's a case of working through the numbers, staying organized, don't get lost. All right. So that's all of Chapter 5, is mostly of your typical buildings covered in Chapter 5. So there's tables like this, where you say, what's the slope of the roof? Less than 10 degrees. What's the ratio of this distance to this, to the height? So in a long building like this, you're going to have high uplift here and diminishing forces as you go along. So you've got to make sure this upwind bit of the roof is stronger. Okay? And then you remember that the wind blows this way, so this bit has to be stronger as well. All right? I'm not trying to make it sound like a nightmare, but it is. All right? There's a few factors in there. So, for example, if you're designing a portal frame and you're talking about the wind in combination on the wall and the roof and the other wall, that's three surfaces at once, you get it to use a reduction factor. If you're talking about a big area, you get to use another reduction factor. If you're talking about a small area, you don't get to use that. And that's basically assuming that, you know, the wind, because, you know, in a big windstorm, the wind blows and it's transient, it's talking about when the major gust hits, it doesn't hit the whole large building all at once. I should actually backtrack and say the wind speed we're talking about in that V, I think we're talking about a 3-second gust. So it's the maximum wind speed that will be sustained for 3 seconds. And that's the definition of that. Correct me if I'm wrong on that, but I think that's right. The next little nightmare, which you don't have to deal with right now for your wall, but maybe you do, is called local pressure factors. Okay? This is the second half of Chapter 5. And what it's talking about is that the wind acts harder in a small area. And you can average it out a bit on a larger area. Up until now, we've talked about the wind on the whole roof. Okay? Now you have to zoom in and say, on a small area, you can actually get an effect which is higher than the pressure we're talking about. And it can be 1.5 times as much. It can even be, in certain configurations, 3 times as much. So the classic example is when you have a house, this is a plan, and you have a roof, which line like that. You guys ever seen a house where the roof is blown off? Or a building where the roof is blown off? Where did it start? The whole thing came off. Okay. If you were watching it, you probably found it started at the corner and it peeled back from there. Because the local effects you get in the corner can be 3 times what you'll see in other areas. Okay? And that area there that I've drawn is a ratio depending on the whole scale of the building. It's all explained in difficult charts and tables there. Okay? So there's a diagram. You can see the RA1, RA2. There's a table which says what they are. And there are things like negative pressure, upwind corner roof with pitch less than 10 degrees, 3.0. Okay, that's that corner I was talking about. So you have to allow for force on the whole structure, and then you have to allow for higher amounts of force on small parts of the structure as well. Okay? All right. Let's go through then. Chapter 6 is all about dynamic forces, so we'll skip over that. And to do the wall, we then look at one of the appendices. Just got to find which one it is. Here we go, Appendix D. Appendix D, freestanding walls, hoardings, canopies, solar panels. Okay? And so we need to figure out the C fig value, that one, for your wall. Okay? I'll leave that up there. Okay. So we draw our wall. Okay, a few dimensions on that. There's your wall, there's the H, which equals 3. There's also a value C, which is that value there. C is 3 as well. If this is a hoarding, if it was a, there's the ground, and there's the sign way up there, okay? C is that height, and H is that height, C is that height, so they're different, okay? Where you have a wall which goes down to the ground, C and H are the same thing, okay? We'll come to that in a minute. Now we can have a force which blows against the wall this way, it's the wind blowing into the wall, and we also have to consider when the wind blows along the wall. Friction can push it that way as well. I suggest that's probably not going to be an issue because walls are naturally stiff that way. Alright, so C fig from D2, C, when I say D2 is Appendix D, Clause 2. C fig equals CPN times KP, where CPN is a net pressure coefficient acting normal to the surface, and Kp is a porosity factor. Alright, and we look at a table here, we can see that net pressure coefficient, hoardings and freestanding walls, wind normal to the wall or hoarding with an incidence of 0 degrees, as in the wind is blowing against the wall. Okay? It's got a B to C ratio. Oh, sorry. That dimension is B. How long is your wall, guys? Sorry? 120 meters. Alright. Okay, so one of the things it asks for on the table is the B over C ratio. Okay? Your B over C is 120 divided by 3, which is about 40. Okay? So B over C greater than 5. There we go, it's easy. And your C over H, B over C greater than 5. Your C over H is greater than 0.7. I'm sorry, that's at 45 degrees. B over C, all greater than 5. Your C over H is 0.2 to 0.1. This is your CPN value, 1.7 minus 0.5 times C over H. Okay. 1.7 minus 0.5 C over H, and that comes from table D2A. Alright, that's our CPN. And that equals 1.7, C over H is 1, 1.7 minus 0.5 is 1.2. Okay? CPN is 1.2. Everyone happy with that? Okay. You can do it again for when the wind blows at 45 degrees to the wall if you want. And the local pressure factor doesn't mean something. That's 1. Your K factor is going to be 1 in this case. You've got an area reduction factor of 1, local pressure factor of 1. So you can use that. Therefore, our pressure on the wall equals 1006 times 1.2, which equals, let's call it 1200 pascals. And that is 1.2 kPa. Okay? So, when you've got your wall here, and there's your person standing beside the wall, and the wind is blowing this way, it's putting a load of 1.2 thousand newtons, kilonewtons, 1.2 kilonewtons on every square meter of the wall. Okay? So if we take a 1 meter wide strip of wall, there's the ground, there's our footing there, we are going to have a load of 1.2 kilonewtons per meter. Alright? So the bending moment at the bottom, shear force and bending moment, the shear force is going to equal 3 times that. So our V star, which is the shear force, is going to equal 3 times 1.2 is 3.6 kilonewtons. And the bending moment at the base is 1.2 times 3 times 1.5. Everyone understand that? 1.2 times the height, which is 3 for the force, times the distance from the lever arm, which is 1.5, is 5.4. And those are per meter length of wall. Okay? So when you're designing a wall, on the footings, the bending force is 5.4 kilonewton meters per meter length of wall. All right, so if you've designed a wall which is concrete panels, which span 2 meters, and you've got steel columns in there, every 2 meters, you're going to have 10.8. Okay, that's the bending force you've got to design those posts for. Does that make sense? Any questions on that? Okay. I just remember there is a local factor. Yes.
When you're doing the CP calculation over there,
Yep.
what happens to the KP part of that?
Oh, KP is 1 for your wall. If your wall is perforated and lets breeze through, then it's got a porosity of less than 1.
Oh,
Yep. Any others? I'm looking for a local factor, but I've lost it. So be happy. Basically, what the local factor says is that at the end of the wall, actually suffers a little bit more load than the rest of the wall. So you have to make the end stronger. I'll let you guys ignore that if you want. Okay. So that is 1170. Print it, own it. If you have trouble sleeping at night, read it. It will give you headaches and heartache in years to come. All right.